Well, good morning. Happy to be here, and I'm grateful to Rosemary that she has invited and forced me to present something. So this brought me at least 1 week of research in my present sabbatical. Well, she also made pressure on me to give some title, and some time ago I didn't really know what comes out there for the question mark at the very end. So I hope we can find out during this talk if it really matters or not. And maybe you could say, who cares? But when I was listening a couple of talks, I mainly enjoyed the talk of Valerie on Tuesday, and I had the impression you could skip my talk now, because everything is old rubbish and unfortunately I don't have such a big box of used ideas in front of my office as Valerie has. But at the very end, in the last 5 minutes, I got the impression that things might still be interesting. So, well, let's see. Okay, this is joint work by Ulrike Grashoff. So she has done the most of these things, and I'm just reusing it. Well, she's now with the Humboldt University in Berlin, so probably next 5 years I have to do the work on my own. Well, but therefore I've hired Heiko now. What is this all about, and what has this to do with healthcare? So when Rosemary asked me, we have some new follow-up workshop on design in healthcare. I said, healthcare? I don't have to do anything with healthcare. And then I went back very far to 10 years ago, that some of our former PhD students, Norbert Bender, who was working then at Schering, a pharmaceutical company in Berlin, approached me to have a common project. And, well, this company was bought later on by Bayer Healthcare, so we have to work in that. We were thinking about which projects could be handled, and this was the initial start. So, and I try to motivate that. So So this chart overlook what I will do. So as usual, there are 5 acts in a drama, and as I have 45 minutes instead of 30 minutes, I add a prologue and an epilogue. Let's see. So this is more a theoretical talk, but at the very end we'll see some simple examples showing that there might be some issues in there. Okay, so this is the starting point. So when we're trying to identify what might be interesting for a PhD project, Norbert Bender came up with population pharmacokinetics. So I said, what? Didn't hear that before, and so we had many of these talks during this week, and he showed me this curve and said, oh yeah, we want to find out how the drug acts, or how the drug is concentrated in someone's body, and we measure these things, and we want to find out where we should measure, and something about non-memory. I want to understand what's behind that. And things are much more complicated, because we have several people and persons are different. And what we want to find out is the typical curve. So then we had a steering committee of scientists from, at that time, Schering Pharmaceutical and Novartis and our person in there, and we tried to identify what might be interesting. And we got a lot of ideas, and always somebody got up and said, oh no, this is all known. Well, so this was a little bit discouraging, but at the very end we decided that we want to find out at least what of the folklore or why the folklore is true. And so then I identified that this problem is too hard for me because all this nonlinear stuff, I could not solve it properly. So I went back, as Valerie did on Tuesday, to the linear model where we can calculate everything exactly. And as I mentioned, I didn't have such a large box of used ideas. I tried to find out everything on my own, or at least with the help of my students. Okay, so just to make clear what I want to talk about is we need some basic notations because everybody uses different notations. So that's the notation I'm now using for the last 20 years. So what we have some observations which depend on an explanatory variable. We have some known regression functions, and later on we will only consider linear regression. So the regression function is a constant and the identity, and then we have some parameters we are interested in. So for the linear regression it's just the slope and the intercept, and some random error in there. And for make it easy, we assume that they are normally distributed, independent, and homoscedastic. And what we want to find out is a good estimate for the parameters. And well, so you know all this stuff you can write down this in next notation. And the thing we should remember is down here is that the covariance is the inverse of the information matrix. Well, so far so good, but well, we have these different animals in there. Or let's remember to remind on Tuesday, maybe different centers. So at each animal, each center has its own curve. And so for linear regression, they might look like that. These are the mean curves, the theoretical ones we can observe. We want to, and we also don't want to estimate. We want to estimate the typical one, which is somewhere in between. And well, how to do that? Okay, so we have to enlarge our model. Go to the well-known hierarchical models. So what we put in is that we have individuals and we have replications, and everything is the same. So nearly everywhere where there was an I for the observation so far, we now put an I and a J besides, and we add an I to the individual parameters, so which give you the personal line in there. And we put on top of that an assumption on the individual parameters, which are assumed to be realizations of randomizers coming from bigger populations. Everything independent. So keep things easy. And just to track you, that you could identify what is what, I tried to use always red colors for the individual things and blue colors for the population level things. Okay, so then you can write down everything. You can split up the random part just to see what's going on. And if you look for the individual covariance, you see that now observations are correlated, so things might become a little bit more complicated. Well, and then there's no real straight line solution. So you could write down what the best linear unbiased estimator would be if you would know the dispersion matrix D of the random coefficients, of the random parameters, which we assume because otherwise it would, that we know it, because otherwise things would be too complicated. So keep things as simple as possible. And yeah, well, so these are the situations, and these are the situations I will look at in my example. So linear regression, and there are two situations. One is a baseline. So the design region varies from 0 to 1. 0 is where I start off, and 1 is if I put the highest dose in there. And the other one is the regression to, or to be more honest, regression through the mean. where I have the design region from -1 to +1. Maybe this is academic, but it shows that there are some things which you have to take into account. I will call this R2M for regression to the mean. Well, and the essential thing why these peculiarities will occur is that the variability of the effect of the slope is assumed to be much larger than the variability at the offset, the baseline. So, in a way, should be described as these curves. And we assume that the coefficients are uncorrelated. Things are so simple. So, what's the solution? Any guesses? So, the first guess is do what you are used to do. So, if we look for, let's say, D-optimality, I don't like D-optimality, but I will look at that because it shows most punctuated what's going on. A-optimality is much simpler, but does not show as many problems. So Valery used A-optimality. Things are much nicer than they are for the D-optimality. So first guess would be just do what you are used to. So these theoretical statisticians, they put half of the observations at the lower end of the interval and put half of the observations at the upper end of the interval. So is that true? Okay, so now we have to simplify again. Well, because if you vary everything everywhere, life is we cannot get any, or I cannot get any analytic solution. So what we did is we first assumed so-called longitudinal designs, which means we are changing the observations within the individuals. But what we assume additionally, to keep things simple, that all individuals are treated in the same way. So this means that we have the same number of replications per individual, and we have the same settings in each individual. So xij is equal to xj, only independent of the individual. So the design measures are then all the same, and also the covariance measures, which are written down there, which will help to make the analysis much simpler. So well, so if you want to estimate, probably all of you know this is quite easy. We can use the ordinarily squares. This is the best linear unbiased estimate. We don't need to know the dispersion matrix in advance. It only comes in the covariance matrix, and as Valery has pointed out, the covariance of the estimate just splits up additively in the covariance here of the standard model without random effects plus the dispersion of the random parameters. So if you have the A-optimality or some linear optimality, then it's fine, because then the criterion is the sum of the old one plus a constant determinant. It's a little bit worse, because determinant of the sum is not the sum of the determinant. Well, good. Okay, so everybody knows what a design is, but I want to stress we are now looking for designs within the individuals, and for a moment it might sound curious. We look for approximate design within the individuals, although we have fixed only not a large number of observations per individual, but we embed it to get some solutions. And the standardized covariance per observation then looks like that. So you have essentially the standardized covariance in the standard model plus something, or so standardized means divided by sigma square. And what's a little bit curious is that the dispersion per observation coming from the random coefficients increases with the number of replications, but nevertheless, this is because it occurs in all replications. Well, and then, so we will minimize the determinant of this covariance matrix, and we can use a general theory, and so then we have the big theory of approximate design, so we get some equivalence theorem saying a design is optimal if it satisfies a certain inequality, which is a quadratic form in the regression functions. So don't think about what are the matrices and vectors in there, the constants. The only thing is they depend on the design, and so you know that your sensitivity function, which is on the left-hand side of this inequality, has to be some quadratic form with a positive definite matrix in the center, so you get well-defined solutions, and you have equality at the settings, so you can identify where to observe. So if you have linear regression in there, for our example, then the left-hand side is just a polynomial of degree 2 with leading positive term. So the maximum will occur at the endpoints. So we are back at what we were before. So nothing surprising, but so let's look at the example. So the regression to the mean, everything is symmetric, so we are where we are. But to get all maybe, so the essential thing, the optimal design is the two endpoints equal weights. But if you have the baseline, then it happens that the d-optimality or the d-optimal design is afraid of looking where it is difficult. So it lays more emphasis where it is easy to estimate. So the weight at the 0 where we have less variation, it gets larger if the slope variation increases, and we get this lower weight at the right end where it is difficult, where we have larger variation of the lines. So these are the weights. There's some formula. The formula is a little bit complicated, so I don't have written it down. So essential is if the ratio gamma, which is essentially the variability of the slope divided by the variability of the intercept plus the error variance divided by the number of replications. If this gets to infinity, then the weight at the right-hand side gets to 0. And, well, I'm not quite sure whether this is reasonable, but that's the optimal. Okay. So far, so good. But then I remember from Tuesday when Valerie said, so we could do only one arm in one center. So they are hard to change factors to the individuals. And in fact, I came across this problem with an engineering surrounding. I said, okay, we have something we have to adjust, and then they have replicated measures. So that's what we have here. So the experimental setting in a cross-sectional design only depends on the individual and not on the does not change throughout. So it's completely different situation, but so Paul says, okay, we do the usual thing. Let's see where we could do the thing and whether it makes a difference. So I assume that there's a constant term, and then what we have is that the design method becomes quite simple because we replicate the same row every time in there, and the covariance matrix observation is completely symmetric, but the correlations depend on the variability, on the variance function associated with the setting down here. So this is a quadratic form in the regression function. Well, okay. So estimation looks, though you can write it down, but it will not help very much. But for comparing designs, you can write down the covariance in this manner. So this is nothing else but the usual information of one observation weighted by an intensity which is in a way inverse of the variability, and the covariance is the inverse of this matrix. And okay, we can try to maximize that. So design again, but the difference is we have now designed across individuals, not within. And this is the standardized covariance per observation, which we would like to minimize, or at least the determinant of that. Then we can write down, rewrite the classical equivalence theorem. And the curious thing is that we have a quadratic form on the left-hand side, and we have a quadratic form on the right-hand side. So might be not so difficult, but it has strong implications. And again, we want to find the maximum of the difference of both. Okay. Well, linear regression, baseline. Well, everything is fine. Use what you are used to use. But regression to the mean, if you want to satisfy this equivalence theorem, you find out you have to require that this ratio, this strange ratio we had already, does not exceed 1. Because otherwise, the curvature of the quadratic forms will flip. You will have a minimum at the endpoints. And that's not as good. So and if you have equality, then you have the strange situation that your sensitivity function is completely flat. It's a constant. So you cannot use any of these things for your algorithms to optimize and so on. Or you have to adjust them. Okay, so what happens if your variability gets larger? Then it is no longer good to look at the endpoints. You have to do something else. And you have to look for settings such that your sensitivity function becomes flat, because otherwise you get some your sensitivity function will exceed the bound. So, and if you try to find it out, you will find out your optimal design have to satisfy that the points are lying on a hyperbola. Okay, that's nice geometry, but doesn't help. So if you look for a symmetric solution, it says, okay, you have to put your observations not at the very end, at the highest and lowest dose, but at something like 1 over square root of this strange variance ratio. And you see, and what you see, if you get this variance ratio large, the points will move more and more in there. This does not look so reasonable. So maybe it's a short interpretation of what's going on. So if you increase this variability, so this is the transformed design locus, and you look for the smallest circumscribing ellipse, this will getting more and more out until it reaches the smallest ellipse, which is the circle here, and then this is the case gamma equal to 1, and then if it gets out, it bulbs, and then you get a larger angle, and then you have, in a way, because this is a design locus for trigonometric regression without intercept on an arc, you just have to look on equidistant points on the whole ellipse with respect to the transformation. And then you can move around, so you can get so the red 2 points are a solution, the black 2 points are a solution, and everything in between. But there are even more. And another nice solution is a 3-point design, where you put weights on the endpoints and something in the middle, which pops up. And find out, if you take the optimal weight, then the standardized covariance variance matrices coincide, and you don't get this problem of getting in a way singular, that the axis came very close to 0, so the weights are not dropping beyond 1/4, so which means 1/4 at the endpoints and 1/2 in the midpoint, and this will have some dramatic difference to the other design, which I did not notice until yesterday evening, 11 o'clock, when I made the calculations. Well, okay. So just short comparison. Use these two models. I introduced baseline and regression to the mean. We use uncorrelated coefficients. We look for a large ratio of these variances, and we compare longitudinal and cross-sectional designs. The optimal one which we found. We want to look how well they perform in the other model. So we notice that the designs are different, the criteria are different, but maybe they are still very good. The answer is maybe. So here are the efficiency functions, and they are not all. Most of them are dropping. But where do they drop to? So this is just the range for gamma up to 100, but maybe they might drop off more. So you see in the right upper panel of the regression to the mean, if you use longitudinal design instead of the cross-sectional, you're already rather low yet at 20% down of efficiency. For the baseline model, you are down to 60%. And if you do vice versa, it's not so bad. You go down to 75% in the baseline model for the cross-sectional design in the longitudinal setup, and to nearly 70% in the regression to the mean model for the symmetric two-point design. If you use this strange hour design with two endpoints and the midpoint, it goes down rather quickly up to gamma equal to 3, and then it restarts to increase again and become very good in a way. So I don't have any explanation for that. Maybe I made some mistaken calculations yesterday, but I'm quite sure that it is like that. So this would be my favorite now. And here's some other advantages, because it's not only reduced to 2 design points. You have the support of 3 designs. You could check for linearity and so on, which is usually criticism for all this optimal design stuff. Okay, and here are the numbers. If you really look what is going on for the variability ratio 10 to infinity, then if you use a longitudinal design in the cross-sectional setup, it will approach 0. Very slowly, but it will at the very end up. So the formula on the left-hand side. Okay, I haven't shown you how the W star looks like, but this is quite ugly. And what's going on in the opposite case? So these designs perform quite well, for a situation that you have chosen the wrong model or the wrong approach. So you have 70% in the baseline model and 70% in the regression to or through the mean model if you use the two-point design, and you have this minimum for the three-point midpoint design at 94% in the R2M model. Well, what's the conclusion? Well, cross-sectional design work well in longitudinal, but longitudinal design may become very inefficient in the cross-sectional setting. Okay. Well, we're already at the epilogue, so outlook. So this was a very simple example, but I guess if you have more complicated, or I'm convinced if you have more complicated situations, things will not become easier. will become worse. So if we have, for the cross-section, if we have more predictors, so we can do something analytically. If we have this diagonal D, if we can treat general dispersion matrix D. So there's an algorithm which was programmed by Norbert Gafke. You cannot use these standard algorithms that will win whatever here because the sensitivity function is so flat, or they do not work quite well. So we can combine some cross-sectional and longitudinal aspects if they are additive and not non-interacting. We can move things to prediction, just to mention the name of Marina, who's doing her defense next week, as mentioned already. But the real question, which we started off, nonlinear models, I don't know anything at all. So feel completely free to think about that. And okay, there's an extra slide. I have to answer the question, which I posed in the beginning, and the message to go. It's not the take-home message. You don't need to take it home. Just to go to the coffee or whatever. So yes, it does. Thank you.
Thank you. So that was true in advertising. We get an answer. Any more comments, questions, answers to the nonlinear question marks? Nothing. Oh, go ahead.
I think we've seen that in the nonlinear case, it seems to matter quite a lot how you do the analysis, and that if you have these longitudinal models, you get quite a large increase in power to identify drug effects and so on. So, and it seems to be much larger than these 60%, or what I guess your efficiency for the cross-sectional design evaluated with the longitudinal model was 70. It was quite high anyway. So
one was square root of 2.
So I wonder if it's not, as you become more and more nonlinear, that you get more and more advantage to the longitudinal analysis. I'm not sure.
I think things will become worse. I'm sure.
I was just trying to. So I was having trouble with the sort of the notation, the way you're talking about a cross-sectional design compared to a longitudinal design. If I'm thinking about a drug trial that would be cross-sectional, let's say a disease progression analysis, you look at somebody's disease status at the start of the study and a disease status at the end of the study, would that be sort of a cross-sectional, and then the longitudinal would be if you take measurements within that time frame, or am I missing the point?
The cross-sectional only means that you fix the experimental setting, so the dose, for example, for one individual. You don't change it through the experiment, and then for the next individual you have another dose, and so on. So you have one setting for each individual, while in the longitudinal you have a couple of settings for each individual, and we assume that they are the same across the individuals.
Any other comments? Yes?
I mean, just looking at the final answer, yes, it does to the question. Perhaps several people might have anticipated that, but in the opposite direction, so that the more complicated longitudinal design perhaps turns out to be the better one. But the conclusion here seems to be that, for instance, if one wants to adopt a sort of, say, robust and practical approach, not too much can go wrong if you do the cross-sectional design. Is that basically an appropriate summary of?
The summary is, if you don't know really in advance how the design will be performed later on, you will have the longitudinal design within the, let's say, study center, or you just have the cross-sectional across, then you should promote the cross-sectional. But if you know how the experiment will be performed, you should use the appropriate design. I only want to stress that you have to look carefully and not just cannot exchange things. Okay, you could expect you cannot exchange things, but in a way, I had the impression that there's some common sense that use the standard designs and this will work well throughout. And it doesn't. Because in the case I compared, one of the two designs was always standard design to use. So maybe it's just academic question.
Any more comments? Otherwise, let's break for a coffee break for half an hour. Thank you.